Hello, welcome to session number 10 in the series Digital Circuit Design using VHDL. My name is Anurag Nigam, and we are exploring some of the things with VHDL using Nexus A7 board, right? And this is a Xilinx RTX 7 FPGA. So let's go ahead and see what we have done. We have done a D flip-flop, we have done a T flip-flop, we have done a JK flip-flop, we have done a ripple counter, we have done a synchronous counter. Now we want to do a resettable counters, right? So let's do that very quickly, and we are going to use the same display. Okay, so here, if you see, okay, here we have got these displays. So what I'm going to do is I'm going to use this four seven segments over here. I'm going to put in a number using these switches, and I'm going to run a counter in the other four segments, and wherever this count equals whatever number I have fed, then the counter is going to reset. So the idea is very simple. I should be able to set a count. I shall be able to set a count for a counter, and as soon as it equals that count, it should reset to 00. And I want to provide one clear for the prescaler over here, this button, and another button on its side I want to use for a clear of that counter, right? So it is very simple. So let's go ahead and design that. So I need comparator first. So I'm going to design a 1-bit comparator. So I'm going to go in here, create a new design source, create a new file. Okay, so hang on a second. Maybe I'm on a wrong screen and you cannot see my screen. Yeah, so sorry for that. Let me switch the screen. Okay, so I'm creating here a new design here, and I had a new file. Call this one as comparator CMP 1-bit, and it will just show you the equality. So if the two bits are equal, then the output should be 0. And what gate is going to do that? Okay, so an XOR gate is going to do that. An XOR gate gives a 1 output when two of the inputs are alike, and when they are alike, it gives a 0 output. So if I take this and I cascade all of them, okay, with the OR gate, all the outputs, then the output is going to be 0 when the numbers are equal. Otherwise, output is going to be high, right? So that kind of comparator I want to make. So I want to make a comparator. Let me see if I'm recording. Okay, so I want to make a comparator which basically is going to do a XOR. So I'm going to just say okay, and I am going to put here my circuits, and I'm going to say finish. Okay, so here I will call this as C1, sorry about that, C1B, and here I want to have received two inputs A and B, and also one more input is going to be PR, which is previous. Okay, and then I'm going to issue one output Q, and or rather I would say uh, here T in, for example, and I would say here T out. T out would be ORing the current output of A XOR B with the previous T in, right? So do I need a Q? No, I don't need a Q. I just need a T out. Okay, so you understood what I'm going to do with this, and this is a form out. And say okay. Once it's done, should show up here, and I'm going to write the logic. So first of all, I'm going to get rid of all the stupid stuff in here. Say VHDL code for 1-bit We will make a more elaborate comparator later on, which will tell you which number is bigger or smaller, even with positive or a negative number or a signed number. We will do that later on, but for now we need just a equality. So we need to make something which is just going to do the equality. So t out would be assigned something OR with t in, and this OR is A XOR B. This is a very simple logic, correct? And then I am going to make another design which is going to be n-bit version of this. So why does it give a problem? There is a problem with this. Oh, I wrote it in wrong place. Sometimes I do stupidity. Control X, Control V. Okay, so now I'm at the proper place. So whenever your file has a issue, it is going to show up as a syntax error in the tree. And when it is done, it disappears. Okay, so now I'm going to do a n-bit comparator. So add sources, and I would say create file, and I will say comparator n-bit. So I guess you understand what I'm trying to do. Okay, finish. Now I am going to use, so see, this is C and B. It is going to receive 8 or rather n-bit word. So this is going to be let's say 7 for now, and it issues TQ output. Okay, this is a scalar out. Okay, so now the next question comes is this 1-bit comparator has to be made into a component, and that component has to go into this package, correct? So we are using this package. Oh, so there is already a synchronous counter, but this counter cannot reset on a fixed count, so that's why we are going to put in a new counter. Okay, so here I'm going to just paste the entity of 1-bit comparator. Okay, so that's a 1-bit comparator, and I make a component out of it in the package. Okay, and some people may say why I am doing display series even. Okay, the reason I'm doing this is I know in most places they don't teach the logic, they just teach the language. Okay, so I want you to know the logic as well as the language, and I want it to be as precise as possible, because I have seen some people used to writing in C and they say counter is count equal to count plus 1. In VHDL I've seen people doing this. So that's not the right way of doing it according to me, because you should be closer to hardware. You should not just say count equal to count plus 1. That's like a C concept. That's a higher level language concept. You are programming in VHDL, so you don't know what this Vivado is going to do. Is it going to give you a very optimized output? I don't know. So I don't want to take that chance. So that's why I'm teaching you how to do the logic. So this is a comparator in the package. I have declared the component. Now here, this is comparator 1 n bit. Now I'll go to comparator n bit. This is 1 bit. Okay, so this is the one, In this, I am going to go and clear these comments, and instead I'm going to put here a library, my circuits, where I'm saving everything, and use a package my circuits.all. Okay, after having done that, all I need to do is write here VHDL code for n-bit comparator. Okay, now I'm going to introduce here a generic, and I'm going to say n is an integer, and with a default value of, let's say, 8. Okay, and this will be n minus 1 down to 0. Okay, so this is the entity. Okay, so in the architecture, what do I have to do? Okay, signal W is std logic vector, and I'll take one more extra, so it will be n down to 0. So that's one extra, then n minus 1 down to 0. And here I will start with W0, and I'm going to start with W0 assigned 0. Okay. Next is I will do the for loop for generate for I in 0 to n minus 1. Generate and generate LP1, and that's it. And then I have to just do, hopefully you are seeing what I'm seeing. Okay, so this is done, and inside I have to instantiate CMP1, so I'll say CMP, and I'm going to pick up this comparator, which is A, B, T in, T out, right? Control C, Control V, port map, A, B, C in, A, B, T in, T out, A, B, T in, correct, and T out. So when this loop has ended, it would have TWN, correct? And that WN is your final T out or Q, right? So this is called Q here, WN. Okay, so basically it is going to be 0 if both all the bits of A and B are equal, then Q would be 0, right? Okay, so we are done with this comparator n-bit. Now I want to do using full adder, using I think using T flip-flop, right? So using T flip-flop, I'm going to do this. So a synchronous counter. So let's look at the T flip-flop in the package. This is T flip-flop, T clock clear Q, correct? So I want to make a synchronous counter. Okay, so let's go ahead and make a n-bit synchronous counter. So I'm going to make a new source, add a file here, and call this as sync count resettable. How's that? Okay, and if I want, I can add n-bit sync count resettable n-bit. and I am going to put it into the same library, and I am going to hit finish. Now here I am going to say sync, okay, count resettable. Okay, so here I am going to give it T clock clear, and I have to have a comparison word for comparison word, right? And it is going to generate the count output. Okay, so it's going to generate a count output, right? And it is also going to generate is it going to generate a clear? No, the clear is coming from the outside, right? So this clear is different from prescaler clear, okay? And it is going to generate its own reset inside or clear inside by comparing with the word. Okay, so I guess this is done. Say okay. And then I just want this comparator and bit also to go into the package. So I'll copy its entity. O, Control C, and this will go under circuits. Control V, and this will become a component, right? And this will be end component. Correct. I will indent it for the clarity of reading it. Okay, so this is a AND bit comparator in my package. Now going to the synchronous counter with reset. Okay, so this is the one which we are trying to make. Okay. And here this is a VHDL code for resettable and bit synchronous counter, and I need to put in that library because I'm going to refer to comparator. So all I have to say here is library, my package name, library name, and then use the package name. This is done. Okay, so this has to be generic, so I will introduce a generic here, which is n bit wide, and it has a default value of 8. Okay, let's look at the comparator. Okay, so this looks okay. Okay, and then n component. Sorry, what did I do? So why is it red? Syntax error near this. Why there is a equal to here? Okay, so this is the entity. Now I have to create the counter. Okay, so for a counter I need again that same W. Okay, and this W is std underscore logic underscore vector. Again, this is one more, so Oh, count is out. This has to be std logic vector. N minus 1 down to 0. And this is a comparison word. This should also be okay, fine. Std logic vector. Okay, so now this will be n down to 0. This is one more, and then I'm going to have an intermediate signal, which would be okay. Do I need a t here? Because t I can always keep high so that the counter is always running. I don't want to freeze the counter. Okay, because I don't have buttons, but I will have two clears. Do I need two clears? No, I'll just have one clear only. Okay, so here I need clear 2. So this clear would be generated from both the clear which is external and the clear which will be when the word equals to count, correct? So this needs to be std logic. Okay, and then okay, then I also need something like C. Okay, fine. Okay, I want to make a synchronous counter, right? So T is for freezing, right? But anyways, I'm going to give it 1. But let's leave T there. Okay, so what I'm going to do is W0 is going to be assigned T, which is the input, clear 2. Okay, so this is T, correct, T, fine. Then I am going to have T input, and then I can put the loop there, LP1 for I in 0 to n minus 1 generate and generate LP1. Correct. So I'm going to instantiate T flip-flops here for this synchronous counter. Okay, so I'll say TFF1 is going to be T flip-flop. Let's look for a T flip-flop. T flip-flop is over here. Right, so I'm going to instantiate, sorry, T clock clear Q. Control C, Control V, port map T, which is going to be WI, clock, which is going to be clock. Clear, now the clear is coming from either the clear or the clear 2 which is generated. So it is coming from C. Clear, T clock clear Q. Q means it is going to be assigned to W I plus 1. Correct? Okay. So now the question comes is, where is C coming from? C is going to be, it has to be generated high. Okay, so it will be coming from the clear, which is external, and clear 2 is generated from the comparator, right? So this one would be, it has to go high, right? No, it has to go high in either case, right? Or not of clear 2. Okay, let's write the logic like this, and let's put this in a bracket. Okay, so the external clear, if it comes 1, then C is going to become 1, and the C becoming 1 is going to clear it. Now if the external comes, clear 2 comes 0, then not of 0 is going to be 1, and it is going to reset this. So the logic is simple. Next is, I am going to say W, I have to give a comparator, right? So I have to generate a comparator. So I'll say CMP1 is a comparator, n-bit comparator. Control C, Control V, and it has a generic map, and the count is n, and then it has a port map, correct? And what's inside the port map? I take the two words, so let's look at the port map. I take the two words A and B and give a Q out, right? So I take A and B, the words I want to compare. So what words do I want to compare? I want to compare W. Okay, but the W is carrying a count, but then here W plus 1 is not generated yet, right? So W, before I even use, so if I have 0, the T logic would be toggle here, clock clear Q. Okay. Eee. This is my output, right? So I'm giving it a wrong place. But then control cannot be. Oh. Oh. Sorry about that. So this is W for the logic for T. Then I will say signal O. That's going to be the output. It will be std logic vector and -1 down to 0. Correct? And I'm outputting this to O I. So OI. Oh, okay. So W I plus 1 would be assigned W previous toggle and the current output. So it will be toggling when both are high. Okay, so that's the concept of a synchronous counter. So the T input is generated for the next flip-flop from the previous flip-flop T and output by ending them, right? So it will keep on doing this till it generates Wi plus or Wn. Okay, so once it has done that, O will contain the count, correct? O will contain the count, and this O has to be compared. So it has to be compared with word, comma O, and it has to generate the output which is clear 2. Correct? So it is going to be reset when the word and O match, then clear is going to turn low. So otherwise clear is going to be high and not of clear is going to be low. So when it becomes equal to, then not of clear will become 1, which means that the clear would be applied to this synchronous counter. Correct? Okay. Now the last thing is count. Count is a out. It has to be assigned O. Correct. I guess we are done with the counter. Okay. So this counter receives the T input, which can be used to freeze it. It receives a clock input to clock it, and all are clocked at the same clock, so it's a synchronous counter. Clear to clear this count when either the external clear comes in or the word becomes equal to the count. It is going to reset to 0, 0, 0. So this logic seems correct, right? So all I'm going to do is I'm going to take this one and convert into a component. Control C and Control V, and I'm going to make this into a component. Correct? And then this one is AND component. Okay, so this is done. Okay, so this is a synchronous counter with reset. Now I need to test it. So what I'll do is I'll have a test display here. Okay, in this I want to run the count between 31 and 16. So what I have to do here is, first of all, I want to run it with a prescaler, okay, which takes longer to generate the clock, means it is a higher time period, so that you can see it clocking, right? Not the same as the refresh. Okay, so I am going to here do a pre 1. So this is a test display. No, I'm doing it a wrong place. Is it? Is the right place? Okay, so other prescaler is inside this one, right? Digital 8 display. So here the clock is 100 megahertz, right? Right. And it has got clock clear and second clear. Okay, second clear is for the count. So I'm going to say I am going to introduce a prescaler. So let's go to the entity of a prescaler. Okay, there it is. Prescaler. Okay, prescaler generic map and T clock clear and clock out. correct? So I go here and I generate here a signal which is going to be a clock signal, CLK CNT, and this is going to be std underscore logic, right? So this is a clock for the counter, and that's what I want to generate here. So I will do here a prescaler. So where is a prescaler? Here it is. Okay, Control C and Control V. Then there is a generic map, right? And this will decide what frequency I want to divide it with. Let's say I want to divide this with a 24, correct? And then there is a port map, and this port map basically has got prescaler. Where is prescaler? Okay, prescaler receives a T clock clear and C out. Okay, so this is for the counter, so it will be T, and what should I put T here? There is no question of T, so I'm going to put here T is always enabled. Clock is going to be 100 megahertz CLK. Okay, clear is going to be clear 2. No, it will be clear only. T clock clear, and the output T clock clear and clock out. So clock out is going to be the clock for the counter, right? So that will be CLK CNT, clock for the counter. So this is my prescaler. Then I am going to do a SYNC1 synchronous counter, and that's the synchronous counter. So Control C, and this synchronous counter is going to have a generic map. Okay, and what is the width of the counter here? It's going to be 16-bit, isn't it? 31 down to 16, right? So that will be 16-bit counter, right? So it will be a 16-bit counter, right? Then it will have a port map. So in this port map, what do I give this? So let's see what's in the port map. Is going to be T clock clear, word, and count. Okay, so T, so T in this case is 1, clock in this case is clock count, clear in this case is clear 2. Okay, T clock clear, word, and count. So the word to compare it would be word which will come from, so it will be word in, right? Word which will come as an input, word in. Okay, and then count. So in this case the count will be word 31 down to 16. So that's going to be the output, and this assignment is then useless. Okay, so what do I have here? I have a prescaler which generates a clock in clock count which is much slower than 100 megahertz. Okay, and then that runs the synchronous counter as clock count. T for the synchronous counter has been set to 1, so it is always counting, you cannot freeze it. Okay, and then clear 2 is basically going to clear this counter, and word in is for comparison, right? Okay, so this part is okay. So word in is for comparison, And what is going to give the output in WRD 31 down to 16. So this is going to constitute a 32-bit word which is going to be fed to the display. Okay, and you don't have to worry about anything because we have covered this in last session. So once check the synchronous counter also. What synchronous counter does is it's going to say that I have W0 as T, and then I have a clear which is a combination of external clear and an internal clear. Then it says for generate loop, it is going to generate the T for the next flip-flop from the previous flip-flops and its output. Previous flip-flop and its previous flip-flop output, it is generating the T for the next, right? And then it says T flip-flop, T clock clear. So clear is a combination, right? Clear and the output, right? And this output is to be compared with the word to generate clear 2, and clear 2 goes in combination with clear to generate C, and then control output is going to be equal to O, correct? That's the output of the counter. Okay, so this looks okay also. So I'm ready to do this. I'm ready to run this. Okay, so I will go to settings and I'll make sure that test displays the, and here also I'm going to make test display though it is not important. Okay, and say okay, and then I'm going to run synthesis. Okay, so no run simulation, run synthesis, but okay, and then I'm going to provide a constraint file, right? So I am going to, okay, let's see what kind of constraint file is there. This is test display .xdc. So here I have got clear 2 and M17, correct? So this looks correct, and then I have got 15 down to 0 as a 16-bit word, and which basically is the standard, and then the assignment. Okay, V10 to J15, which basically is the switches, which are 16 switches. Then we are looking at T10 to H15 as data out, right? So that's correct. And then we are looking at control CNTL. Okay, U13 to J17, that's correct, as in the case of previous, right? So everything looks okay in the terms of constraint also. So I'm going to enable this constraint file. Okay, I had written this earlier itself. So only difference from the previous one was the adjustment of another switch, which is for the clear 2. Rest of the things remain the same. Okay, so now I'm ready for synthesis. So I'm going to run synthesis. So launch. If things go bad, this will not complete. So let's clear this one. It's running synthesis right now. So I'm showing you the constraint file for the first time. The way you are used to looking it is like a IO here, and you put in these things, and when you save this, it generates this constraint file. Constraint file is nothing but the logical mapping with the physical pin, and also the standard, which is going to be 3.3 volts CMOS. Okay, so now this is done. I don't want to look at the synthesized design. I will just run implementation. Okay, so it's going to take a little time, but hopefully there are no errors. Warnings are okay. There's only one warning. I'm going to turn on this guy. Okay, so by the time this is happening, let's provide an input to our board, right? And let me just show you the board here. Okay, so what I'm going to do is I'm going to feed in 2A, or rather I can put here 1 0 0 0 0, right? So let's say 1 0, everything is else is 0. So what I'm trying to do is I'm trying to count to a hex of 1000, right? On the right hand side it will display that. On the left hand side I'll have a counter running. Okay, so let's see how it's going to work. Okay, so let's see what this guy is doing. Still running synthesis. Okay, okay, I guess it will be done in any minute now. Okay, so I think in one session I can show you just one example. That's too bad. Generate bit stream. So it's going to generate the bit stream. So I am not able to increase my speed, right? So I have already started generating the bit stream. Okay, so it says over here at the top right, says running write bit stream. Okay, so it's too bad that I'm taking 1 hour for one lecture or one design. After this it will be easier. I think I'm going to do a multiplier after this. This is a resettable counter. Hopefully it will work. Okay, so how is this VHDL design different from what you do using transistors? It's more or less the same. That's why I had a playlist on digital circuit design using ADS. You can go to that and see what is the logic for all this, right? So that once you are clear with the logic, you can do structural designs, unlike the high level synthesis which people do and then leave it to the simulator to or the synthesizer to synthesize this and optimize it for you, and they say count equal to count plus 1. I don't believe in that kind of designs. Okay, I guess it will be done in a second. It's done. I'm going to open the hardware manager. So it's connecting. I'm going to open the target device, my board. It's done. Okay, then I'll say program the device and say program. So I should see 1000 on the right, and you see that the counter is already started running. So let me, oh, I am in a wrong spot. Okay, let me show you that. So once I have done the burning, I'll go function F12. Okay, so probably now you can see what I'm seeing. Okay, so I have entered here 101000. So on the right hand side it is showing 1000, and when this count becomes equal to 100, right, then this is going to reset on its own. Or you can clear the counter from here. You can, if you press this one, it's going to clear it. So I'll let this count to 1000. Okay, so it is going slow, kind of slow. How about I put you on pause and let it count to 1000 hex, and once it's done I'll put you back on, right? And then once it crosses 1000 it is going to become 0 again. So I wanted to show you that only. So this is a hex counter which is up counting from 000 to a number which you specify using this 16-bit switch is here, right? So whatever you put in here, the counter will count to only that and then reset back to 00. In most of the microprocessors you will have these counters, right? You feed in a count and it counts to that and resets it, right? So this is one of the components which can go into a microprocessor, right, or microcontroller, right? It's a timer. Okay, so let me put you on pause for a second. Okay, so currently the count is this EC something, right? And I'm waiting for a moment it becomes FFF. After that there will be 1 0 0 0. At that point the counter is supposed to reset to back to 0. So let's see if this is going to happen. So right now we are running F, right? It should become F F F, 3 F's, and the next state will be 1 0 0 0. So when the next state comes 1 0 0 0, the counter should reset to all zeros. So let's see if that happens. So it's FC, FD, FE, now anytime, FF, now is back to 0, you see. So it has compared the count here to FFF, and the next state comes is 1 0 0 0. As soon as 1 0 0 0 comes in, it is going to reset internally to this number, right? Now if I want, I can choose a smaller number. Let's say this is 4, this is 4, and this one. So let's say as soon as it becomes 100, it should reset. So it will become FF, right? As soon as it becomes FF, it is going to reset. It got reset. So you understood that I can feed in any number. At this point, of course, it is counting because that state will never compare unless it goes all the way around to 0 0. I can clear this. Now I have all the switches as 0. Now the counter is stopped because it is always getting reset. It is because the word, the terminating word is 0 0. So it is resetting. So let's say the terminating word I increase to 4. So now it will count up to 4 only, or make it 8. So it will count up to 8 and reset, right? So now let's say I make it 16. So it will go up to F and then reset. Let's make this 20. So it will go up to 1F and reset. Okay, let's make it 40. It will go to 3F and then reset. Right. Let's make it 80. It is going up to 7F and then reset. So you can set any number on the right hand side and it will reset at that point, or you can also press this clear button. So if you want, you can clear this, start it again. So this is a clear for the counter. Now if I clear the prescaler, then the count will stop. Okay, but then it will count from where it stopped, right? So the count has stopped. So let's say it is reaching 450 or 51. So I stopped it. So right now prescalers are not running. So means the counter is not running. Even the refresh display is stopped, right? So if I release it, it will start counting from F2, 52, sorry. So you see that. So one clear is for the prescaler, for the refreshing of the display. Other clear is for the counter. You can reset the count, right? Okay. So this is one small application. Now what I want to do is I want to close the hardware manager and I'm going to put in a multiplier, right? So what I want to do is I want to take two 8-bit numbers on the right hand side of this display and multiply them, and the result should be displayed on the left hand side of the multiplication, right? So let's do that. So what I'm going to do is I'm going to just bring this down a little. Okay, so I'm going to close the hardware manager. Okay, so first of all I'll do a combinational circuit, which is a multiplier, which will be also called a fast multiplier. So there are other ways of doing the multiplier also. So I'm going to demonstrate how it's going to multiply. So it's very simple. Let's say I take a word 1001, which is 9, correct? I take a word and I multiply this with 1101, right? So what do you do? Okay, you do very simple stuff. Okay, so what you do is you multiply the number by itself, and then the next time, so hang on a second. Okay, so you take 1, multiply the number with itself, and next time is 0, you multiply the number with 0, right? And this one basically goes to the output, and then what you do is you add here one more 0 here, and then you add these two numbers, correct? So that's what you are doing. You add these two numbers, and then what do you have? You have here addition of these two numbers, right? So that's going to come up as, sorry, okay, so this will come up as 0 0 0, and this will be 1, and this will be 0. Okay, so add this number, and then to this, okay, what you are going to do is, so you added this and carry 0, then you multiply this with 1, so here it will be 1001, right? And you are going to add these two numbers, correct? So you're going to add these two numbers, leaving the one on the left. So when you add these numbers, what do you get? Hang on a second. Okay, so when you add this number, you get here 1, and here 1, and here 0, and here 1. Okay, so when you add this number, this is what you get, and then you are going to take this one is going to go to the output, and then you are going to again add 1001 to it. So this one again goes to the output, and then you are going to do add this number again. Okay, so when you add this number again, what you have 1 1 as 0, and then 1 is carried over, and then this 1 comes here, right, and this 1 comes here, correct? And then to this you are going to add your other numbers from the other ones. So this is going to be 1, then next one is going to be 0, and then the next one is going to be 1. Okay, so this is your output. So what did you do? You took 9 and multiply this with D, and this is the number you are going to get. So let's do a calculator. Okay, let's see if I'm recording this. Yes, I'm recording. Okay, so I'll put a hex calculator. I'm taking a number 9 and I'm multiplying this with D. Okay, so this is 7. You can see this is 0 1 1 1, this is 7, and then this is 0 1 0, this is 5. So what are you doing? What you are doing is you are taking this number ending with each digit of B. So let's say this is A 1001, and then you take B and you are ending each time you are ending with the bit of B. Okay, and then what you are saying is I'm going to add them, and that generates a carry of 0 here. Okay, next time I'm going to do is whatever is the next number, which is 0 times of or end with zeros, so this will be odd zeros, and then you are going to add these 4 numbers now, and this one will go to the output queue, right? So how many times? So this is an n bit number, so this is, let's say, 4-bit number. So you are having additions. How many times are you having additions? Okay, so you are having addition 1 time over here, 2 time over here, and 3 time here. So you need 3 adders for a 4-bit multiplier. And what about the output? Output is going to be, if the input is n, the output would fit in twice of n, right? So if I put 8-bit number, it's going to give me a 16-bit number, right? So the logic is very straightforward. All you have to do is you put it as a VHDL code. So I'm going to do that. So what I'm going to do is, and this is all the information, like, you generated type and all that is going to show up here when you write a multiplier. So what I'm going to do is add sources, and here design source, create a file, and here I will call this as multi n bit. So this is a multiplier n bit, and here my library, and say finish, and here I'm going to say mun bit. Okay, and here I'm going to take a n bit number a and b, which I'm going to multiply, and let's say they are 7 down is 0. Then I'm going to generate output, which is going to be q, which is going to be out, and it's a combinational circuit. You don't have anything else other than this is going to be 15 down to 0 because it is twice of 8. So 16 is twice of 8. So you're going to say okay, and once it is generated, okay, so I'm going to open this one, and here I'm going to write a multiplier. So okay, I'm going to get rid of all the remarks here and say this is a VHDL code for multiplier for n bit multiplier. So you see what is the benefit of keeping generic? the benefit is I can, if I'm designing a data path and I have a multiplier, I can fix the width of multiplier to be the width of the data path. So with just one n, I can change the, I don't have to redesign it. I can just scale the the data path by any number of bits I want. Okay, so that's how scalable designs work. So here I need to use adder, right? So I need to use the library, my circuits, and then say use my circuits dot all, because if you remember, we have done the full adder and bit adder, right? So in earlier lectures we have, or earlier sessions we have done and bit adder. So do I see adder and bit? Full adder, adder and bit. So we have a adder and bit here, right? So we have to make a multiplier. Okay, so having done that, I have to introduce a generic here. So this is going to be generic, and this is going to be n, which is an integer, and it has a default size of, let's say, 8. Okay, and then this will be n minus 1 down to 0, and this will be twice of n minus 1 down to 0, twice of n, so it will be 2 times of n. Okay, so what do I need for this? Okay, I need 2 types, so I will declare a type here, type, and I will say this as array, is type arr is array. Okay, you can say 0 to n minus 1, okay, of std logic vector n minus 1 down to 0. Okay, oh, there is an underscore here. Okay, so this is one type. I can create another type, INTAR, or I can say added, okay, not added, INTARR, okay, is array 0 to n minus 1 of std logic vector n down to 0, because if you see this one, the added numbers are 5-bit wide. You see, added numbers are 5-bit wide, while the all other numbers are 4-bit wide, right? So I need n down to 0 this time. Okay, n down to 0. So I have 2 of them. Correct. So now I will declare the types signal, ended. So this is ending, right? Signal ended is of type ARR. Correct. And then signal added is of type int ARR. Done. So we are done with this. So now what I'm going to do is, first of all, I am going to populate a ended with ending operation of A with the bits of B. Okay, so I will do a LP1. Okay, and this for I in 0 to n minus 1. Correct? Generate. Okay, and then say end generate LP1. Okay, so here I have to tell you one thing. You can think about this only if your brain is flexible enough. And how it becomes flexible? Because it becomes flexible because you can reason. You use your brain to reason out something's complicated, so it becomes flexible to see all this what I'm seeing. Okay, so now what I'm going to do here is I'm going to do a LP2. So I'm going to do a nested loop. Okay, for j in 0 to n minus 1, or yeah, each bit you have to operate, right? And I would say generate and end of generate LP2. And I'll tell you why these high level synthesis has been developed. The high level synthesis or system C or any other form of high level synthesis, because people are coming from computer backgrounds, right? So they are used to saying that counter is equal to count plus 1. They are not used to using T flip-flop to do a counter. Similarly, if I say multiplier, then all the software guys are used to A into B and equal to this. But you know that in hardware it doesn't go like that, right? Of course you can synthesize with q is assigned A into B, but this is a high level construct. This is a behavior. And then the synthesizing tool Vivado is going to struggle to understand what you wrote. This is not a C design. This is not what a program on a compiler does. This is working with ones and zeros on the hardware level. So you need to twist your brain to do that. Now what do I have to do here? Okay, I would have to take ARR or ANDed, sorry, ANDed. Okay, and every bit which is I is keeping account of the row and j is keeping account of the column, right, will be equal to a, okay, a j, correct? A j has to be, so for all j's it has to be ANDed with bi. Does it make sense? Okay, I can fill it this way. Okay, so I'm filling okay, I could have written this for less confusion. I can say j is going from n minus 1 down to 0, right? So basically j is tracking the entire word of a. Okay, so a goes from n minus 1 down to 0, and then bi, so every column is being filled, right? The first column is going to be b0. So if you see here, the first column will be all the inputs 1001 of a, which are ANDed with b0 to give the first column, right? So when it is ANDed with this, it returns 1001, right? Right. So the second one would be all zeros. So let me just do this. Let me just change the color so that you can understand that. So this one, let's say make it blue. Okay. So this is B. And this one, let's make it red. This is A. So when you OR this, okay, so the first word is going to be 1001. Okay, so that will be placed in the first one, and the second one will be when you OR when you end with 0 is going to be that, and the third one would be this one, and the fourth one is going to be this one. Correct? So this is what I am filling, right? So this is what I'm filling here. Okay, once you're done with this, you are going to start with filling the first one in the added. So you will say A D D E D, and its MSB is going to, first of all, its column is going to be 0, and second thing, its row, its row is going to be 0, and the column, which is going to be the nth bit, right, that has been supplied with the 0. Sorry. So first time no carry is generated, right? Okay, now I have to fill the next one. Okay, so how do you fill the next? Okay, other bits. So other bits would be added. Okay, and this one would be. So do I have to fill it? Let me try to see it. The first one I'm going to fill. Okay, that's fine. First one I'm going to fill. So this will be the 0th row, and this one will go from n minus 1 down to 0. Okay, so this I'm going to fill with the first from ended. So ended 0. Correct? So this is done. Now I'm ready to write LP3 for I in, I'm going to go column wise, 0 to, not 0, because first one 0 I have filled already, 1 2 n minus 1, generate, right, and then say and generate LP3. Correct? So in this case I have to add the number, so I have to instantiate a full adder. So I'll say FA1, okay, is a full adder. So let's see a full adder here. Sorry, n bit adder, right? So adder n bit. So this is what I'm going to instantiate here. Adder n bit. Then there is a generic map. And the width is going to be n. And then there is a port map, right? And the port map receives A, B, two words to be added, C in, sum, C out. Okay, and of course C in is always 0. So I'm going to receive A, B. So I'm going to receive added I minus 1, right? And then this one, which will be added I minus 1. This is going to be the 0th row of added. And then I'm going to go n minus 1 down to 0. So this is my first word I'm going to add. And this is going to be added with the second one of ended. The second one will be I. Okay, and then C in is always 0, right? And then A, B, C in, sum and C out. Okay, so it is going to generate a sum. Sum will be going to added. Okay, and added, it will be the ith one. Okay, and then it will be n minus 1 down to 0. 0. And then the carry would come in added ith one and the nth one. So here the carry is going to come. Okay, so I'm done with this. Okay, so when it is done, it will go to filling and it n minus 1. So now one more thing I need to do is I need to do a Q, the output, right? So where is the output here? Output is called Q, small q. So Q of I minus 1 is going to be assigned added I minus 1 0. So Q is collecting your output, and then finally once it is done, then I will say Q is twice of n minus 1, right? Okay, so I will say finally Q of twice of n minus 1 down to twice of n minus 1 down to n minus 1. Okay, so this is going to be n plus 1 bit, right? So this is going to be like 5-bit wide, and that is there in the last added. Okay, added the last one. The last one added would be added n minus 1. Correct? So this is a very simple code of a multiplier. So first we will check if it in simulation it is working, and if it is working in simulation, then I am going to display this. Okay, so I can use the same constraint file because it has a clear 2, and I'm not going to use clear 2, so it's not going to cry, is it? I don't want to write the constraint file again. Okay, so what I'm going to do is, first of all, I'm going to disable this constraint file first. This is for the test adder, right? Second thing is I'm going to set the multiplier to be the top level schematic. So I am going to set the multiplier as a top. Okay, so the multiplier becomes a top level. Now I am going to go to sources, and under general you see multiplier n bit, simulation, multiplier n bit. Say okay. So let's see if I'm recording this. Okay, 24. Okay, fine. So now I'm going to run simulation. It's not going to cry, is it? Let's see if it cries. So logically I have done everything correct to give me a multiplication. Okay, so it did. Okay, So don't worry about this extra stuff. You just have to focus on A, B, and Q. So let's say I set A as 2A. 2A. This is my favorite number. And the second one I set as, so first of all, let's reset this. Okay, so first one is 2A. Okay, and the second one is 3C. So let's force this constant, sorry. 3C. Okay, it's 2A, 3C. And let's simulate this. Oh, oh, I did a mistake. The mistake is I haven't assigned Q. Everything is going in O. Is it? Okay, let's see if Q is not assigned. Q is assigned according to me. Okay, so let's just close this. Close simulation. Let's try to debug this out. So why ended and this is not filled? Well, let me put you in pause. Okay, so it's very easy to spot this out. You see here, it says, okay, let me see if I'm recording. Okay, so this is a stupidity. Okay, the stupidity goes that n minus 1 down to 0. It should be down to, right? It should not be 2, 0, right? So now this is correct. Let's run this simulation again. So sometimes mistakes can be very stupid. Sometimes mistakes can be very stupid. And if you know how to debug, it is going to be very fast. Debug this. So let's see if this is really what the matter is. So I'm going to go here and I'm going to say force constant 2A. Hopefully this should work now because I haven't done any mistakes. 3C. And if I hit run, so you see 2A into 3C, which is wrong. 3C is ended right. This is ended right. So this is two of them as 2A. Then 3C. Right, 4 of them are A. And then I'm ending them, right? After that I am adding them, right? Okay, answer should be something else. Let me just figure out. CALC. I know the answer is wrong. Hex 2A into 3C equal to 98. Okay, so the answer is not 98. So let's see what has happened. So I'm going to put you again on the pause. Close simulation. Close the simulation. Okay. Hang on a second. Okay. So now it's very simple. I figured it out. Now if you remember here, I have a shift here, right? So my previous term is going to be 0, 1, 0, 0, and this 1 is left out, right? So this 0, 1, 0, 0 is from n down to n down to 1, right? So in here, this I have taken as n minus 1 down to 0, should have been n down to 1. right? So now everything looks okay to me. So you just save it, and then let me see if I'm recording. Some warning came up anyways. So we are done with this. Now let me see. Okay, let's run this again. Okay. Oh, I'm running synthesis. Cancel that. I have to run the simulation only. Run simulation. Okay. Okay. Okay, so we are back to where we were. And I'm going to put in numbers here. Force constant 2a and force constant 3c. 3c. And of course I have to do this. Oh, come on. Okay. So let's reset this. Okay. So here I'm going to force 2a and I'm going to force 3c. Okay. And then I'm going to say run. Okay. So what do I see here? I have 2a, 3c, and the answer is 98. So let's bring up our calculator and say hex and say 2a multiplied by 3c. 98. So answer is 98. Now let's try some other numbers. Let's say I want to try ff multiplied by ff, and the answer is fe01. Okay, so let's put here ff ff multiplied with ff. Okay, and when I say run, the answer is fe01. Okay, so the answer is fe01 over here, and here you can see the answer is fe01, right? Okay, so basically that means that this multiplier is working fine. So I'm going to close simulation. Okay, now I'm going to try to do this on the board to see if synthesis is working. Simulation doesn't mean synthesis. Okay, the major unknown here which I face is I have a type declaration inside my architecture. So if synthesis tool accepts this, it's going to work. So I am going to go back to test display, and I'm going to make it the top level schematic. Okay, then I am going to generate this multiplier. I am going to generate a component for this multiplier, right? So this multiplier, I'm going to copy the entity, Control C, and I am going to paste that entity in the package and make it a component. So I'm going to paste this over here and component. Component. The only issue is that type declaration is not global. The type declaration here is local to the architecture. So that's why I am in doubt. And let's get rid of the doubts by synthesizing this. Okay, so multiply n bit is I'm going to instantiate. Okay, so this is I'm going to instantiate in my display. Test display. So in test display, if you remember, we were doing a this thing. Okay, so I'm not going to do that, right? So I don't want this stuff. So I don't want this word. So I don't want this one. Correct. So this prescaler I don't want. Okay, I also don't want the synchronous counter, right? Okay, so I don't want the synchronous counter. This is for the previous exercise. Now I have the word which has got two inputs, so I want to instantiate a multiplier. So I will say mul1, that's a multiplier, and I want to instantiate this guy. Correct? Control C, Control V, and then it has got a generic map. And that generic map, I'm going to put 8-bit wide input, and then say it has got a port map. And this port map is going to receive two words. Okay, let's see. What are the two words? A, B, and Q as the output. Okay, so A in this case is going to be the input word in. Word in. And this would be going from n minus 1 down to n minus 1 down to, sorry, n minus 1 down to n, to n minus 1. So I can directly write yn minus 1. I can say this is 15 down to 8. Correct? And the second word in will be, word in would be 7 down to 0. So these are the two words which I entered, and the output will be WRD, and this would be 31 down to 16, isn't it? 31 down to 16. Okay, what's the problem? No problem. Okay, so I am instantiating a multiplier which is 8-bit wide. It receives word in 15 down to 8. So this is going to be 8-bit word. 7 down to 0, another 8-bit word. And 31 down to 16 is 16-bit word. And then 15 down to 0 is the word in itself, and then the display. And the issue is here the clear. Okay, if you want, you can go ahead and change the constraint file, because there is no clear here, right? In this signal there is no clear here. So what I can do is I can remove this clear. I don't know if this is a good idea. Fine, so I don't have a clear here, but in constraint file I have a clear. So I can go ahead and modify the constraint file here to remove the clear 2, right? So clear 2 is this one. Okay, so set property clear 2. So this is the property of clear 2, and then this is the clear 2. Okay, rest of the things remain the same, so I'm just going to save this, and I'm going to enable this guy, enable this file. Okay, so now I'm not very sure. Okay, everything looks okay. Everything looks okay in simulations, but in synthesis, I'm not sure. This is what I'm doing, right? what did I do here? I am taking a multiplier, instantiating it, keeping the output to a word and giving it to the display. Here I want to check that my general is test display, and simulation I'll still do a test display, though it is not required because I'm starting from synthesis. I'm not starting from simulation, so everything is fine. So I'm going to say run synthesis. Okay. So hopefully everything will be okay. So I'm going to put you on pause till I do synthesis. Okay. So I'm going to clear this. There are no errors here. Okay, I'm going to put you on pause. Okay, the synthesis is complete, and that means that nothing went wrong. Then I'm going to run implementation and put you back on pause. Okay, so even implementation is complete, so nothing went wrong. Now I'm going to generate the bit stream, and I'll put you on pause. Okay, so now the bit stream is generated. Open hardware manager, and device is already on. Open target, auto connect. So no problems till now. Program device. Okay, the device is programmed. Now let's say if I have 2A and 3C. So this is 2 and this is A. So first number is 2A multiplied by 0 is 0. Then I want to do 3C. Okay, so this is A. So then this is 3. So 2A with 3 0 is 7E0. Okay, and 3C, this is C. Okay, so 2A multiplied by 3C is going to give 9D8. Okay, so if you remember, calculator clear 2A multiplied by 3C is equal to 9D8. So the answer is 9D8. 2A multiplied by 3C equal to 9D8. Okay, now let's try to give some other input. Let's say 3F. 2A into 3F is A56. So let's see this on the calculator. Okay. Okay, so we are on the calculator right now. Okay, so my inputs are 2A multiplied by 3F. 2A multiplied 3F equal to A56, and I will put the screen on that one. Okay, so now you can say 2A into 3F is A56, and that's what my calculator is also saying. Now 2A into 3C is equal to 9D8, right? So last time I didn't show it. Okay, so now see 2A into 3, hang on, 3C. 2A into 3C is 9D8. So the answer tallies with what calculator is doing, right? 98. So now you can say that the multiplier is working fine. Now can I, and then, so of course, you know what I'm doing? I am doing the test for the display, and I'm giving the output in 15 down to 8, 15 down to, 31 down to 16, I'm giving the output, and then 15 down to 0, I'm giving the input. So where, you know, input is divided into two words, which will be 15 down to 8 and 7 down to 0. Okay, so that's what's going on here. So I'm already taken 1 hour 46 minutes. I have shown you multiplier. Now I can do a instantiate adder, which is going to be 8 bit, and I can do a adder. Subtractor is going to be very similar, so maybe probably next time I'm going to very quickly show you the both of them, and then proceed further to process and subprograms, functions and procedures. Now process is still used in synthesis some places, but functions and programs, I'm not sure how helpful they are going to be, right? Though these constructs, which are going to be in sequential in nature, are going to be used a lot in your testing, right? So from synthesis point of view, okay, I would have reached the limit here, okay, of explaining you what these VHDL objects are, and then I will give you a brief on testing and move into testing. But I want to cover IP block based designs also. So probably I'll finish on the subprograms and the process by the next lecture, and from there I will go to the IP based block designs. Okay, thanks a lot. Thank you very much.